All right, so here we have a induction problem, number 10 from chapter 20. So hey, in this problem, we have a magnetic field. So here's the magnetic field is going into the page, and it's got a strength of 0.15 Tesla. The loop is grasped. Oh, and we have the radius of this loop. The radius is given. R equals 0.12 meters. You want centimeters to be into meters. And what they say is this. The loop is grasped at point A and at point B, and at point A gets yanked upward, point B gets yanked downward. Now what's that going to do to the loop? If it's a nice flexible loop and you grab the top, pull up, grab the bottom, pull down, what's going to happen to this loop? It's basically going to shrink to zero, right? It's going to close up. So this is going to cause a change in flux. So the big idea for this topic is this. It begins with flux. So magnetic flux is the product of three things: the magnetic field, the area of the loop, and then the cosine of the angle. So this theta, that's the angle between the B field and the normal line to the loop. Okay, the normal line to the loop is sticking straight out of the page here. Okay, what they want us to find, if it takes 0.2 seconds to close this loop, they want us to figure out the induced EMF. And EMF is a fancy name for voltage, right? Like in Ohm's law, we said delta V equals IR. That's the same thing as saying E equals IR, where EMF is this symbol E. So how do we find this induced EMF? Well, here's the idea. The induced EMF, the equation for it is this. Here's the equation. So N is the number of loops. How many loops do we have here? Just one. Cross this out to 1. Now in this problem, yeah, like for a problem like this, you look at it and they don't mention that it's a coil. There's not like more loops behind it, so you can assume it's just one. So it's one loop. Now there's three different ways. So you see right here, this is change of flux. There's three different ways to change the flux. Some problems it's going to be the magnetic field changing. Other problems it's going to be the area of the loop changing. And then other problems, you're going to see the angle between the normal line and the magnetic field changing. In this problem, what's causing the flux to change? The area. So I'm going to write the change in flux. I'm going to write it as B delta A. Wouldn't that be right? The change in flux, you're going to take the field, which is not changing, and then multiply by the change of area. And then that's going to give the change in the flux. And then divide that by the time, and then that gives the voltage. Now, you got to calculate the initial area of the loop. The initial area of the loop, you just go pi r squared, where this is r right there. The initial area of the loop is 0.0452 meter squared. Now, what's the final area of the loop? 0, because it says right here, it's stretched until its area is nearly 0. So we go from having an area to having 0 area. So what's the change in area going to be? 0.0452. Okay, so the induced voltage, we're going to take the field. We're plugging into this equation right here. The field is 0.15 Tesla. The area of the loop is 0.0452 meter squared, and then we divide by the time, which is 0.2 seconds, and then this comes out in units of joules per coulomb, which is volt, and we get an answer of 0.034 volts. That is the induced voltage in the loop, and it's almost like this. I mean, literally, you can imagine it. It's almost like there's a battery in this loop that induces, that drives the induced current. Now, next thing, the question doesn't ask for this, but how would we find the induced current? What would we have to know? We'd have to know the resistance of the loop. So let's just say, let me revert this. Let's just say that the resistance of the loop is 0.05 ohms. Okay, just pretend they gave that to you. What if they wanted you to find what the induced current was? Well, you would go, well, we found the induced voltage. The induced voltage was 0.034 volts. If we had the resistance of the loop, how do we get the induced current? E equals IR. So I is going to be E over R. 0.034 volts divided by the resistance, which would give what is it? 0.67 amps. So that's how you would find the induced current.